In today's video, we'll continue to use our knowledge about first and second derivatives and what it tells us to help us in certain problems. We want to find A, B, and C in this particular equation, knowing the following information. If 1,4 is the local max, and there's an inflection point at x equals 1/3. Well, let's start out. If 1,4 is a local max, that means the point 1,4 is a point on the original function. That means in f of x, or I guess we have y here, in y, we can put 1 in for x and 4 in for y. Okay, and again, we can do that because 1,4, because it's a local max, is a point on the actual function. Because 1,4 is a local max, well, we get local maxes and local mins. We determine that from the first derivative. So we should be able to also determine something about y prime. Well, if at 1 is where the max occurs, that means in the first derivative, when you plug in 1, it should give you back 0. It's a critical number. So by the fact that 1,4 is the local max in y prime, we should be able to put in 1 for x. And because it's a max, that means we should get back 0 for y prime. Now, the third piece of information is if there's an inflection point at 1/3, we know inflection points we get from the second derivative. Well, it's pretty similar to what we just did for the last one for the max. If there's an inflection point at 1/3, that means that x value of 1/3 should make the second derivative 0. So in y double prime, we're going to put 1/3 in for x and 0 in for y double prime. So we know what y is. Let's see if we can find y prime and y double prime. Now keep in mind, a, b, and c are constants. It's like a 2 or a 7 or a 14. So ax cubed, the 3 would multiply out front to give us 3a, and now we'll have x squared. Plus 2b, and we'll just have x plus c. If we take our second derivative, the 2 will multiply out front to give us 6ax, and we'll have plus 2b, because the c is a constant. Derivative of a constant is 0. Now we have y prime, and y double prime to do what we just wrote in the black. We said, for the first one, we're going to put 1 in for x and 4 in for y. So we're going to have 4 equals a times 1 cubed plus b times 1 squared plus c times 1. And we'll neaten that up over to the right. That will give us 4 equal to 1 cubed is 1 times a is just a. 1 squared is 1 times b is just b. And c times 1 is just c. Next, we'll work with our first derivative. We said we're going to put 1 in for x, and we should get back 0 for y. So in our first derivative, we'll have 0 equals 3 times a times 1 to the second plus 2 times b times 1 plus c. We'll again neaten that up off to the right. We'll have 0 equals 1 squared is 1, so we'll just have 3a. 2 times b times 1 is just 2b, and then we've got plus c. And the third one, we'll put 0 in for y prime and 1/3 in for x, so we'll have 0 equals 6a times 1/3 plus 2b. Neatening that up, we'll have 0 equals 1/3 times 6 is 2, so we'll have 2a plus 2b. What we've now created is we have a system of 3 equations with 3 unknowns. We were missing a, b, and c in the original equation. However many variables you're trying to find, or unknowns that you have, a, b, and c in this case, that's how many equations you have to set up. If you have 2 unknowns, you need 2 equations. 3 unknowns, we need 3 equations. To solve this, we want to somehow, with these 3 equations, be able to write 2 equations with just 2 unknowns. Well, notice we already have one of those in the third one, so I'm just going to rewrite that down here. We've got 0 equals 2a plus 2b. We need to somehow create another equation with just 2 unknowns out of these 3. To do that, what we're going to do is we're going to take our first equation and subtract from it our second equation. Kind of like what you do when you're doing elimination. The reason we will do this is we'll be doing c minus c, which will take the c's away, and then we'll have an equation with just a's and b's. So we'll start out, we'll do 4 minus 0, which will give us 4. Next, we'll have a minus 3a, which will give us negative 2a. We'll have b minus 2b, which will give us negative b. And we'll have c minus c, which is 0. What this has now created is 2 equations with 2 unknowns, and we can just do our regular old elimination. Notice it's already nice. We have a 2a and a negative 2a. Go ahead and add your equations. You get 4 equals 2b minus b will give us b. So we just found that b was equal to 4. Now, just like when you do regular elimination, we'll put that 4 in place of b in one of our 2 blue equations here to find a. So maybe in the second one, we'll have 4 equals negative 2a minus 4, because we're replacing the b with 4. Add the 4 over, and we'll have 8 equals negative 2a. Divide by negative 2, and you get that a is equal to negative 4. So we've now found 2 of our variables, or 2 of our unknowns, a and b. Now go back to one of your 3 original equations and find c. Probably the easiest one is that top one. So we're going to have 4, which was already there, equals, we know a is negative 4, we know b is positive 4, and we don't know what c is. Again, that's just from plugging in right here. Well, this will give us 4 equals, negative 4 and 4 will give you 0, so 4 will just be equal to c. We've now found what a, b, and c were. Remember, the original was y equals ax cubed plus bx squared plus cx. If we put those all in now, this means our actual equation is y equals negative 4x cubed plus 4x squared plus 4x. If you wanted to check, you could check and see that our point 1, 4 is on there. You could check and see if 1, 4 is a max, doing things like we've done on the previous videos and in previous classes, and you could check to see that 1/3 is an inflection point, again, by doing your second derivative. We'll do one more example that's similar to this. We're now going to work with the general equation y equals ax squared plus bx plus c. We'll again find a, b, and c, but they've given us different information. They tell us 3, negative 10 lies on the graph. We have a tangent line at negative 2, negative 5, and at that point, there's a slope of 9. So first off, we know 3, negative 10 is on the graph. So that means in y, we're going to plug in 3 for x and negative 10 for y. Well, then they tell us negative 2, negative 5 is where the tangent line is occurring. Well, the tangent line is where it hits the graph. So that means negative 2, negative 5 is also a point on the graph. So it's going to be very similar. we'll stick with in y because it's on the actual graph. We'll plug in -2 for x and -5 for y. Now the third part, it says at that tangent point, we're going to have a slope of -9. Well, your slope of your tangent line is the y value of your derivative. So in y prime now, we're going to plug in -2, because that's the x value it's occurring at for x. And we should get back the slope value. So we'll plug in 9 for y prime. Now in the previous example in our derivative, we plugged in 0 for y prime because that's where a max was occurring. And at a max, your slope of your tangent line is 0. So we'll put -10 in for y in our original. Actually, I guess we should find y prime first. Notice we don't need y double prime for this particular problem. Y prime is going to be equal to 2ax plus b. We'll plug -10 in for y in our original. And we'll plug in 3 for x. We'll have a times 3 squared plus b times 3 plus c. We'll plug in -5 for y, and we'll have a times -2 squared plus b times -2 plus c. And then the third one, we'll plug in -2 for x and 9 for y prime in our y prime equation. So we'll have 9 equals 2a times -2 plus b. Now we'll neaten those all up. 3 squared is 9. 9 times a is 9a, so we're going to have -10 is equal to 9a plus 3b plus c. Then we've got -5 is equal to -2 squared is 4, so we'll have 4a minus 2b plus c. And then we have 9 is equal to, we have -2 times 2, which will give us -4a plus b. So just like last time, we now want to turn these into just two equations with two unknowns. And we already have one of those. We have the 9 equal to -4a plus b. And just like before, we'll subtract these two equations. When we do that, -10 minus a -5, that'll give you a -5. 9a minus 4a will give you 5a. And 3b minus a -2b. So minus a -2 will become a +2, so we'll get 5b. Probably the easiest thing to do to get these to match up is to multiply the top by -5, giving us -45 equal to 20a minus 5b. And we'll just rewrite our -5 equals 5a plus 5b. And now we can do elimination with this, adding them together. -5 and a -45 will give us -50. We'll get positive 25, and the b's will go away. Divide by 25, and you'll get a is equal to -2. Plug back into either one. I'm going to plug back into the top one. We'll have 9 equals -4 times -2 plus b. That's 9 equals 8 plus b, so b is equal to 1. And we've got to go back to the ones that have c in it. Maybe we'll do that bottom one. Negative 5 equals 4a minus 2b plus c. And it doesn't matter which one you plug it into. So we'll have 4 times negative 2 minus 2 times 1 plus c. That'll be negative 5 equals negative 8 minus 2 plus c. That'll be negative 5 equals negative 10 plus c. Add your 10 over, and you'll get 5 is equal to c. So we have a, b, and c, our three unknowns. Put it all together as your equation. We had, as our original, remember, y equals ax squared plus bx plus c. So we now have y equals negative 2x squared plus, you can put the 1 in if you want, or you can just write it as x, and then plus 5. And if you wanted to check, you could check to make sure that 3, negative 10 was on your graph, negative 2, negative 5 was on your graph, and that your derivative, when you plugged in negative 2, gave you back a value of 9, meaning your slope was 9 at that point. For the last one for today, it's going to be in your packet, and we're going to be on page 3. So you can take a second to pause the video until you get that packet page out. Now, when you're given a graph, it's important to always note what graph you're working with. We are working with an f-prime graph. We want to end up with a f graph. The interesting things in our f-prime graph are where those roots occur and where the maxes and mins occur. The roots are significant. That's what we normally put on our number line when we're doing our first derivative test. The maxes and mins are important because those will be where the next derivative, the second derivative, will be 0. So in this graph, our significant x values are a, b, and c. A and c because that's where we have roots. B and c because that's where turning points are. So for our intervals that we're going to look at, and you can start them off to the side if you need some more space because it's a little tight. We're going to look at from negative infinity to a, because that's the first unique point. We'll look from a to b, from b to c, and then we'll go from c to infinity. Now what we want to put in the next two columns are positives and negatives. We want to know what are the y values of our graph in that section. Well, for f prime, we can just simply look and see what are the y values because we have the graph right there. Well, negative infinity to a, that's this whole section. That whole section of graph has negative y values. The next section, we're looking from a to b, so this section here. That whole section has positive y values. From b to c, this section here, we still have positive y values. And from c to infinity, still positive y values. Now, what that will tell us about f, we're going to skip a column and jump to f, is whether it's increasing or decreasing. Because the sign of your derivative tells you if your original slopes were positive or negative. So that tells you if you're increasing or decreasing. So we know in this f column, our first interval was decreasing, and the next three were increasing. Now for f prime, whenever you want to find the values in terms of positive or negative of the next derivative, you always have to look at the slopes. So we'll look at our slope from negative infinity to a. Our slope in that whole section is always positive. From a to b, our slopes are always positive. From B to C now, though, our slopes are negative. And then C to infinity, our slopes are back to positive. Now remember, our second derivative tells us concave up, concave down. So this will help us with our last column there. When f prime was positive, we'll be concave up. So the first two are concave up. The third one is concave down. And the last one is concave up. Now we can use this to help us. Let's start with the f prime. The only time the f prime changes sign is at A. At A, it goes from negative to positive. If you go from negative to positive, you should have a min. So another piece of information we know is that there's a min at A. Our second derivative, when it changes sign, that's where we have inflection points. Well, those are changing sign at B. At B, we switch from positive to negative. So we're going to list that we have inflection points at B. At C, we switch again from negative back to positive. So we've got two inflection points. And we're going to use this now to sketch a graph of f. So we'll mark roughly where A was, where B was, and where C was. We know we have a minimum at A. So let's just pick some y value. We don't know where, but let's make it down low because it's got to be a minimum. We'll also have inflection points at B and C. Now, because we're increasing the whole rest of the graph from A all the way to the right, wherever we pick our inflection point for B, say it's here, we need to make sure we pick our inflection point for C somewhere higher than it, because it's increasing the whole way after A. So just like when we do with other graphs, we'll draw in our concave up, concave down sections, and we'll check it with the increase, decrease. So we are concave up from negative infinity to A, and then when we continue concave up from A all the way to B. So basically everything left of B should be concave up with a minimum being at A. So we'll have something that looks like this. Then we switch to concave down from B to C. So it will now appear something like this. And then it switches back to concave up after C. And we'll use our increase, decrease to check. So negative infinity to A, we are in fact decreasing. And then the rest of the way, we are always increasing. That's all for today's video. We'll see you next class, period.